Okay, so now what I want to do is calculate my cross product. So what I'm going to do is calculate that cross product vector by adding a new attribute, which is going to be a vector again, and I'm going to call this one n, which will basically give me the resultant cross product vector and show it to me in the normal. At the moment there is no normal attribute to it, so if I just visualize this quickly, there is no normal in there. If I add a normal, however, then you can kind of see over there, there's a normal attribute. At the moment it's 0, 0, 0, but we will be calculating our cross product. So if I just call this one cross and just so that I know this is where my cross product is. So what I'm going to do is I'm going to add my cross product for a custom vector and for a position. And then I'm gonna write an if statement in my value and choose between the two depending on my dot product, right? So in my edit parameter interface, I'm going to add two parameters. The first one will be, well, they will both be vectors, so I need a float vector 3, yeah? And I'm just gonna drag and drop it onto the root, yeah? Another one, drag and drop it onto the root, and the first one I'm going to name cross, and let's do, say, for the position first, and I'm gonna say this is going to be the cross position, yeah? So this will use the position of the vector of the particle. Alright, apply this, and then for the second one I'm going to say I want to have cross, and I'm gonna say custom, yeah? So cross custom, okay, and apply that. So these cross underscore pos and cross underscore custom will become important later when we will be referencing those channels. So let's accept this. So I've got two new positions there, cross position, cross custom. So again, just like when I was sort of explaining the maths on how to build up that cross product expression, now we're actually going to start building that up. So first of all, I will be needing a cross between the two vectors. Which vector? Well, I'm going to be needing it between the velocity, well, not just the velocity, but the velocity that I calculated before, which was the last good velocity. Yeah? So let's say vector 3, yeah? Dollar last good velocity, so I named that LV, and I'm accessing the X component, dollar $LVY, the Y component, dollar $LVZ, the Z component. So basically this will give me the velocity vector even if the particle is stopped. Yeah, it will still use that, the last known good velocity vector. And the other one that I want to use is the position. So vector 3 again, vector 3, and let's get the position. So dollar $TX, dollar $TY, and dollar $TZ. Okay, so this will return a vector. One more thing that I want to do with this is I want to normalize these guys. So first of all, let's put a normalize around them, normalize, and normalize. And since this is the first component, the final thing to add onto is that little indicator. So if I just bring this up into an expression editor, you can kind of see the entire expression. So we've got the cross product between the last known good velocity and the current translates x position of the particle. That will give me the resultant perpendicular vector between that plane, and then that vector is normalized, because this guy is not normalized. It's just the last good velocity, and the position is not normalized either. And then from that normalized vector, I'm going to use the first component, which is 0, the x component. So I'm going to apply this, accept it. And then for the other one, I want to do the same thing, just change this to 1. And the last one, change this to 2. Okay. And again, basically the only thing that I need to do there, the cross with a custom, is I'm going to copy this entire first expression, so from the x value. And let's bring up our expression editor. Make sure that it's empty. Now, instead of using over there the tx, yeah, I'm going to use, instead of cross position, cross custom, I'm going to use my custom vector. So I remember that my custom vector was cvec, there, cvec, this is the way it's written. So I'm going to put that in there, so let's write this cvec like this. Yeah. Don't need t, cvec there, and cvec there. Yeah. And again, the first component is fine for the x, so copy this entire line, just say apply, accept. Yeah. Let's put it, oh, I didn't copy it properly. Let's have a look. This entire line, copy, tab, copy it in there, and let's change this component to 1 once more for the z, and change that component to 2. Right. Okay, so now I've got my cross position and my cross custom, and now for the value I need to start deciding. The way to start deciding is by using my dot product, so that dp value, so if I just quickly bring up that spreadsheet, the value that I'll be using is that dp over there, which was being calculated between the original velocity and the position. This dp will decide basically if it's going to be using the position or if it's going to be using a custom vector. Okay, so I'm going to start writing an if statement. If, yeah, $dp, that's my dot product result. If this result is basically, say, bigger than 0.95, yeah, so if they line up, yeah, then I want to start using my custom vector, yeah, because I don't want to use my position vector because it's going to give problems if it's, you know, sort of close to 1. So my custom vector value needs to go in there. So the way I'm going to do this is by using the channel, yeah, so reference that channel that I just created. If I hover over this one, it should give me the, there we go. So that's the parameter is cross custom x, so you can kind of see it over there. Well, anyway, I just need to get that channel. So I just need to type this in, cross underscore custom x, the x component of this, and that is the case, again, if this value is true. There, oops, wrong one. Alright, for the last argument of my if statement, I want to say, okay, if it's false, which means if they're not overlapping, then use the position. Then it's fine to use the position. So, again, reference this, and I name this cross underscore, and I believe it is named, come on, it is named, so cross pos x, yeah, so you can kind of hover over it and see the parameter cross pos x. That's what I need. Cross pos x. Yeah. And let's apply this. And we need to apply this now for the other channels as well. So this is going to be a vector, so we need to apply this for the y channel. In this case we need to say, okay, cross custom y, and for the y channel there as well, use the cross of the position in y. One last time, and let's do it in z. So there we go, in z and in z, like this. Yeah. And this will, or this should give us a resultant vector. So there is a little resultant normal over there. You can kind of see already the normal is kind of sticking out of this. Yeah. So in the beginning it's going to give a problem because, again, like I said, the position is 0. But as soon as it goes up, it aligns itself to always kind of find, you know, that cross product. Yeah. And that's the cross product we need. Yeah. Okay. Again, if we would not have this force in there, and it would just go straight up, yeah, it should still evaluate. Yeah. So you can see over there, it gives a perpendicular vector. Yeah. It's not the same as before, but it does give a perpendicular value because at the moment the dp, yeah, so the dot product, yeah, is equal to 1, and the resultant vector of this one will start using the custom, so we'll start using this one. So because it's equal to 1, you can kind of see over there that, you know, that normal is giving a correct kind of perpendicular normal to the velocity. And even if I keep on playing this, even if the velocity goes to 0, yeah, it's still giving that vector, which is good. That's what we want. Okay, so now we're gonna have to start using, after our split, we're gonna have to implement all these attributes using a VOPOP to calculate sort of the spread. Yeah. Yeah. So let's create a VOPOP, and we can go inside. And we're just gonna rename this and add, so say like perp velocity. So this will add a velocity to it each time they've been splitting. One more thing, I want to add this perpendicular velocity to my split group. So not to the base, but to the particles that have split off. And I'm going to go inside. There's my output. And what I need to do is I need to get some of my axes and some of my attributes inside. So first of all, the global variables. What I want to do is, as these guys split, based upon their ID, I want to give them a random rotation. So I'm going to be needing a random. And I'm going to plug in the ID to get the random number out of this. And this random number will basically drive a rotation operation. So I'm going to need a rotation as well. So this is the angle, right? So if I would just say this and plug in the random number, so the random number will be a number between 0 and 1. If I plug that into the rotation, then the rotation will give me sort of an incorrect value, because this is in radians. So I would expect a number instead of between 0 and 360. I need a value between 0 and 2 pi. So I need to multiply whatever comes from there with 2 pi. So let's add a multiply constant to this. And there in the expression I'm going to type $pi, which is a constant, times 2. It's the circumference of the circle. So now I'm sort of starting to define one slice of the circle, in this case a random slice. That's the easiest to start off with, and then we're sort of gonna add some attributes and start to divide this up into sort of a ratio and equal slices. Okay, I'm going to get my axis. The axis that I want is going to be my veloc. So if you remember, the velocity that I wanted was, first of all, if the particle stops, I still need to have that velocity, so I still need to have that axis to rotate about. So I'm going to be needing a vector there. The axis should also be normalized, so I want a normalized axis, and I'm going to say veloc. There. I'll just label that as well, and just one more veloc. And I'm going to plug this into my axis. Like this. And then the result of this should be multiplied with the normal. So the normal that is coming on these particles, since everything is inherited, if you just see, I'll just add my force on again. Because in my split under my attributes, I said inherit attributes, and all of the attributes are inherited. The normal attribute, which I created just above, which has the cross information, will be inherited by the child particles, and now I'm going to be using that inside of my VOPOP network. So if I play this and it flies off, so okay, it's got two groups now. It's got sort of information. So this bunch of points, they're all light on top of one another, but they're normal information I can start to use to kind of rotate around the velocity axis. So this normal will have to be multiplied by that rotation value. So I'm going to do is lay down another multiply. Okay, so let's use the normal, and let's use this rotation result. Now you might notice that this rotation matrix is purple and this is green, which basically means that this one might potentially be from a different, it's a 4x4 matrix. But since I'm just using it for rotation, so just using basically the 3x3 section, I'm not using any translation. Translation would basically use a 4x4. And it's just using a rotation. This won't give a problem. Yeah? And then the product, so the result of this, I want to plug into my velocity. So if I plug this into the velocity, and let's rewind this, make sure that our display flag is on the last node, which is our VOPOP. So sort of there, and let's rewind this and let's have a look. Yeah? So bam. Yeah? So as you can see at the moment, if I just turn this off, it's randomly kind of creating these circle-like patterns based upon that cross product. Yeah? Now, one more thing that I want to do in this area, sort of, is make sure that my new normals are not going to sort of be lying flat on that grid. Yeah, as you can see there, and they're sort of, you know, really flat. Wouldn't it be nice if they would just inherit that original velocity? Because if they do, then we can start to use them afterwards to calculate our tangent velocity. So let's go about and let's do that. So what I need to do is just get my velocity over there. Yeah, this is a normalized attribute, I know, because I created that attribute, and I'm going to plug that into the normals. Yeah? And if I rewind, then you'll see now, see, all of the normals are sort of, you know, inherited from that initial particle, yeah? And they're only being inherited when they are being born. So the current normal of this particle, yeah, the current velocity, is not being transferred, and that the reason why that is because it's only being applied to the split group. Yeah? Okay, so this is quite useful. This could already, you know, like be sort of used in the sub level to kind of copy spheres on, and you can kind of see the result of this there. So you get this kind of, you know, spheres randomly copied on. But what if we don't want them to be randomly copied, but what if we want them to be copied sort of in an even spread? Yeah? Alright, so we're gonna have to make a little bypass and calculate sort of an index and a maximum number of points in the current split group. And the way we're gonna be doing that is through subs. Yeah? So I'm going to save it here and do this in the next section.